Hello and welcome to the video about projectile motion with launching at an angle. This goes along with assignment 5.3. We're going to talk about all sorts of different things that deal with the projectiles, but this time let's begin with going back over where we had left off last class. So recall from last class that when we shot a cannon or anything else horizontally, it would have a initial horizontal velocity. Also recall that because that velocity is not being affected by gravity in the x direction, that horizontal velocity stays the same the entire path of the projectile. However, when we look at the y velocity, notice to begin with, Vy is equal to 0, but then it increases at a negative 9.8, negative 19.6, negative 29.4, negative 39.2, negative 49. A couple things here that I wanted to emphasize. The reason that Vy is negative is because it's going down. Okay, so it's important now that we're in projectiles and we're looking at motion in two directions, x and y, that we really have a good sense of what's positive and what's negative. And this can confuse some of the equations, and it can really screw up your answers. So in general, if an object is going up or there's any upward motion, then that's positive. Towards the right is also positive, just like on a number line. Going down is negative, and towards the left is negative. So those are the sign conventions that I will be using on these problems and that are pretty typical to use throughout physics. So this is what we saw last time with just a horizontal launch, the increasing velocity in the y direction based on the fact that there is a gravitational force pulling downwards on the object. So now let's go take a look at what is actually happening when we don't have a horizontal launch. So when we don't have a horizontal launch, notice, as you can see here, that's drawn here, at the initial part we have an initial velocity of v. Okay, we call v or v naught our initial velocity. And the initial velocity is at some angle. At some angle equal to theta, and that theta is going to change throughout all of our problems. So when we have that initial velocity where theta is not equal to 0, so it's launched at an actual angle, we really have to be careful here, because just like before when we launched it horizontally, we have to deal with the x components and the y components. If we talk about the x components alone, Vx is still a constant, just like it was before, because gravity hasn't changed just because we're launching it at an angle. And it is still, according to this picture, going to be equal to your original total velocity times the cosine of theta. And this is key. You've got to remember to find your Vx when you're launching at an angle. Similarly, Vy is equal to V naught sine theta. However, this is Vy naught, or V naught y, I guess is how I would typically write it. V naught in the y direction. And the reason why we have to be specific that that's V naught in the y direction is because as it goes up, it will change. And, oh, sorry, I noticed there's a misprint here now. This should be a Vy, and this should be the Vx. So the Vx does not change, but the Vy does change. It starts out nice and big here, then it gets smaller, and then at the very top, notice that Vy is equal to 0, and the only velocity you have is Vx. Then it's going to come back down again, and Vy is going to increase and going to increase some more. Now the key thing here is that this is a symmetrical situation. And so let's take a look at a simulation. Notice on this simulation, this is at a simulation center called Walter Fend. It's out of Germany. And so here we have an initial height of 0 meters. The initial speed is 15 meters per second. We're going to launch it at a 45-degree angle. We're going to say we're launching a 1 kilogram ball, and gravity is normal gravity. So this has already calculated for us the y and x speed components. And we have a time, and we are going to show the velocity arrows, and you can see the red line for the path. So let's watch what happens. This is let's do regular speed first. Okay. Let's do that one more time so that you can see really focus on the y velocity arrow. It's getting smaller, 0, and then comes back down and gets larger, going in the negative direction. Because gravity is the only thing causing the acceleration on the projectile, it is the only thing that's going to influence the acceleration. And because gravity is a constant, it's the only thing that's going to influence the velocity. And because gravity is a constant, then the change in velocity is going to be a constant. It's going to decrease first, and then it's going to increase. And notice that the whole time the x stayed the same. Let's do this one more time, but let's do it in slow motion so you can really see what's going on here. This is now 10 times slower. If we look at the values up the top, we see that the y is decreasing down to 0, and now it's increasing in the negative direction, whereas the x is just staying the same the whole time. Also notice that the magnitude of the overall velocity is changing, and then when we get to the very end, right when it hits the ground, its magnitude at the end is exactly the same as the magnitude at the beginning. So the size of the final velocity, total final velocity right before it hits the ground, is going to be the same as the size of the total velocity right as it is launched. This, of course, is assuming that we have a perfect situation where there is no air resistance. Okay. Now, if I get rid of the velocity and I just look at acceleration, and we don't need to see this in slow motion, and we set it. Now, this is the acceleration vector. Notice it's pointing down the whole time. It never changes because it's always gravity. We can change our angle. Okay, so let's change that angle to 25, and let's see what happens. Acceleration stays the same, but notice what happened to the distance. Okay, let's do it one more time. The range got significantly larger, but the maximum peak height decreased drastically. Let's go back to the angle being 45, and let's look at the range. Notice the range is about, what, 23, and the height is about 1, 2, 3, 4, 5, between 5 and 6. Whereas if we go back to 25, the height drops significantly to about 1.5, maybe 2, and the range increases to 15, 16, 17, almost 18. So when we change our angle, we can tell that it has an automatic effect on both the range and the height to which it travels. So if we watch this one, again, notice a change in velocity in the y direction. Okay, so now let's come back to our drawing here, and let's put out some things, talk about some things that we can now determine by knowing this. All right. Number one thing is that we already said we can determine the x and the y velocities based on just trig, but there are some other things that we can determine too that will allow us to solve these problems. Well, one of the things that we always want to be able to determine is the time in the air. When we talk about the fact that we're going to determine something about this and the time in the air, we have to really understand what's going on. Projectile motion is symmetrical. Even if we don't start and end the projectile at the same height, so even if we throw it up at an angle and let it fall all the way down to the ground, it is still symmetrical. So the speed of the ball at the height, when it gets back to the original height that it was at, will be the same, even though it will continue to increase its speed as it falls the rest of the way to the ground. So if I add on to this picture over here, I can add on, for example, here, I can say that we have an acceleration, which is equal to gravity. At this point, we also have an acceleration equal to gravity. At the top, not only do we not have a y velocity, but we still have an acceleration equal to gravity. All the way throughout, we have an acceleration equal to gravity. This speed here on the left is going to be the same as the speed on the right. So if you know that at some point in time your projectile has a speed of, say, 15 meters per second at some point in time in its path, chances are there's going to be 2 points in time that it has that speed. One on the way up, one on the way down. Okay, especially if we're starting and ending at the same height. So because it is symmetrical, what that means is the time it takes to go up is equal to the time it takes to go down. So if we use the equation, v final in the y is equal to v initial in the y plus at, and we say that the v final in the y is 0, meaning that it's at the peak up here, then we know that the time up is going to be equal to a negative v naught y over acceleration. But your time can't be negative, but it's okay that this is in this equation it's negative, because remember, acceleration is gravity and gravity is pointing down, so that means that it is a negative number. So acceleration is gravity and it is a negative 10 meters per second squared. So a negative divided by a negative is a positive, which means that our time up is equal to v naught y over 10 here on Earth. If for some reason I decide to give you a problem where it's not on Earth, then you have to remember that the time up is v naught y over your gravity. Okay? So there's our first thing that we can determine using with projectile motion and using the kinematics equations, the time up. The second part of that is to remember that the total time is equal to twice the time up, because time up is equal to time down. Okay, so t going up is equal to t going down. All right, let's see what else we can determine. All right, so we also need to be able to determine the range. Remember, just like it was before, the range is the distance traveled in the x direction, and just like it was before, the x velocity does not change. So your x is v naught x times t. That's always the same. And this t is the t total. Okay, keep that in mind, because typically you're going to be solving for just half of this. You're going to be solving for t up, and then you're going to have to multiply it by 2 to get the t total. The other thing that you're often asked about is the peak height. How high did this ball go before it came back down again? And we often call this y max. So how high does it go? Well, keeping in mind, again, kinematics equations, y is equal to v naught yt plus 1/2 at squared. If this is at a y max, then this means that t is simply t up, not the whole thing. And remember that acceleration is a negative 10 on Earth, or meters per second squared. So you have to remember that it's really a negative gravity. So in this equation, when we put this in, we find that y max is equal to v naught y t up minus 1/2 times gravity times t up squared. That minus sign is crucial. Don't forget about it. Whenever we're trying to solve a projectile motion problem, we have to think about these things, but all of these things rely on the fact that motion in the x and y are independent. Which means that they do not affect each other. Yes, the x speed will affect the range, but it does not affect the y speed, and it does not affect the y max point. And in fact, it doesn't affect how much time it takes either. The velocity in the x only affects the range, whereas the velocity in the y affects the time and the maximum height that it travels at, just like we saw in the simulation. All right, let's do an example problem here so that you can see how this all fits together and it might look, and then you'll be able to go ahead and solve the problem, do the worksheet. All right, so we have a projectile launched with an initial velocity of 50 meters per second at an angle of 20 degrees from the horizontal. Make sure that you know whether it's from the horizontal or from the vertical, because that too will change your problem. Let's find out what is the maximum height that it reaches. What is its range? How far does it go? And what's its time in the air? How long was it up? Well, let's draw a quick diagram. Always, always, always draw a diagram for these things. So here's my ground. Whoops, a little bit crooked there at the end. There's my projectile path. This angle is 20 degrees. My initial velocity is 50 meters per second. I don't know my range. I don't know my I don't know my max height, and I don't know the time it takes for it to travel this path. But I do know enough things to get started on this and to solve it. So for example, I know the initial velocity is 50 meters per second. So from this, I can start by solving for the initial y velocity. The initial y velocity will be 50 sine 20, which if we plug that into the calculators becomes about 17.10 meters per second. I know the initial x velocity is 50 cosine 20, which is 46.98 meters per second. So most of the speed is in the x direction, which means that the range is going to be fairly long. From this, I want to find the time first. It's always a good place to start, is to start with your time. So using the equation that I figured out earlier, I know that the time up is going to be the initial velocity in the y direction divided by gravity, which is 10 in this case. So 17.10 over 10. So the time up is 1.71 seconds, which means that time total is going to be twice that, which is 3.42 seconds is the total time that it's in the air. So from that, I've got that one. Let's go to the range. The range is the next one to do because it is also super simple with the fact that range is just simply the velocity in the x times the total time. Velocity in the x was 46.98. The total time is 3.42. Now again, these further calculations depend on your first calculation, so make sure you get that one correct, which also depends on your calculations of v naught x and v naught y. This becomes 160.68 meters. So that's our range. To find the maximum height, I'm going to use the equation of v naught t plus 1/2 at squared, keeping in mind that it's v naught y t up plus 1/2 at up squared, which will be 17.10 times 1.71 plus 1/2 times a negative 10, because gravity is the acceleration and it's in the opposite direction of the motion, so it has to be negative, times 1.71 squared. So 17.1 times 1.71 is 29.241. 1/2 times a negative 10 times 1.71 squared is a negative 14.328. So the total maximum height that this projectile reaches to is 14.91 meters. Okay, so in this one problem, you're given just the initial velocity and the angle, and from that you can figure out everything else that you could be asked about this. This should get you started on assignment 5.3. So good luck and bye for now.